Okay, so this time we want to go the other way around, and we want to take a derivative, the picture of some function's derivative, already created the derivative and wound up with this graph, and we want to take this and say, well, what are some things we know about the original function f if f prime looks like that? Okay, so just to kind of review where we've been here, let's look over here. This was the f prime that turns into this f because this was the f that we said looked like this f prime. So notice that these points where it crosses the x-axis correspond to flat zero slope tangents. So the -2 and the 2 were where f prime of x was 0. Okay, so this is a little different from the one that we created, but we can assume that our result should be similar to the f in terms of its shape. But we've got a 0 at -3 and a 0 at +1. Okay, so if f prime is 0, then here's what we need to find out. We're going to use the graph of f prime to find intervals where f is increasing, decreasing, and then give the x-coordinates of the local extrema of f. Well, that's what we just annotated here, is the local extrema of f, because this is where it flattens out. Now, f is increasing when f prime is positive or greater than 0. F is decreasing when f prime is less than 0. And then the local extrema, we'll worry about whether it's a max or a min later, but the local extrema occur when f prime equals 0. The only thing we haven't accounted for up here is when f prime is equal to 0. So well, we can see that pretty easily here. We've got on the interval from -infinity until we hit -3, we've got f prime is positive. It's above the x-axis. Now from -3 to 1, f prime is negative below the x-axis, so f is decreasing. And then we're back above the x-axis here after 1, so from 1 the rest of the way to infinity, f is increasing. Okay, so we also know that we go from, say this is 0. Okay, so I don't really have to worry much about what's going on the y-axis. I don't really know much about that. But I do know that from -infinity to -3, we have increasing behavior for f. And then at -3, we have a slope. So if we're increasing, and then after -3, between -3 and 1, we're decreasing. And then after 1, we're back to increasing again. Okay, so I know that I'm going up, and then I flatten out with a slope of 0 at -3. And then I'm going down, and I flatten out with a slope of 0 at 1. And then it's increasing again. So let's get an f that's increasing up to -3. And it's decreasing to +1. And then it's increasing again. So this could be f of x. Okay, right? Because my slope, f prime said I'm above the x-axis, meaning f prime's positive. So these are all positive slopes till it hits the -3 where f prime is 0. That's my slope of 0. And then it's negative, so my slope is negative throughout here of the tangent on f. Flattens out at 1, and then it's positive again. So I don't really know what the outputs are, so I'm not going to label that. I just know it's increasing, and we know that this is a relative max. At x equal -3. Okay, we knew it had either a maximum or a minimum. The reason we now know that that is a maximum is because if we're increasing and then we start decreasing, we topped out there. If we're decreasing and then we start increasing, we bottomed out there, making this a relative min at 1. Oops. Okay, so let's see, we answered everything here. Intervals where f is increasing, decreasing in the x-coordinates of the local extrema. Okay, and we said there's a local max at -3 and a local min at x is +1. Okay.